Welcome to video 9-5. This is about properties and conditions for kites and trapezoids. I'm on page 471 in your text, 471, and we're going to talk about a kite here really quickly. We know what a kite is, as we can see, from what is flying in the sky sometimes. But a kite is actually a geometric shape that has specific properties to it. So here's our definition here at the top of our Explore, and that is that a kite is a quadrilateral with two distinct pairs of congruent consecutive sides. So consecutive, remember, is one right after another. So as you go around the figure P, Q, R, S, we're going to look at two sides that come one right after another that are congruent, and there's two pairs of those. So in the diagram here you can see that PQ is equal to PS and QR is equal to RS, but we cannot say that there's this consecutive pair, PQ and QR. You can see the different tick marks there. So there's certain conditions that and certain properties that apply for kites, and that's what we're going to explore here in this video. Let's go to the next page. If we go down to the bottom of that page where we're talking about the relationships that are true in a kite, we want to make sure that you're highlighting these four conditions, four theorems about a kite. If it's a kite, then first off, it's kind of like a rhombus in that its diagonals are perpendicular. If it's a kite, then one of those opposite angles are congruent, and you can see that that's the angle Q here and angle S, those opposite angles. Notice P and R are marked with different types of tick marks, so they are not congruent to each other. Notice also that angle Q is not split into equal pieces on either side, and neither is angle S. You can clearly see different sizes of those angles there, whereas angle P is got two congruent bisected angles there, as well as angle R. So that's the next one. One of the diagonals, the next theorem about kites, is that one of those diagonals bisects the pair of that are not congruent angles. So Q and S are the ones that are congruent. The other two, P and R, get cut in half by this diagonal that runs from top to bottom, or in this case left to right. Through those angles, it cuts them in half. Finally, the theorem that we need to know is that if it's a kite, then one diagonal bisects the other. So thinking about what these diagonals do, in a parallelogram, remember, they're going to bisect each other. That's not how this works. In this case, only one diagonal, this one, PR, is going to bisect diagonal QS. So you can see that the smaller pieces QT and TS are congruent. So what we're going to do is on the next page we're going to use those relationships to figure out some missing angle measures in the kite. In example 1, we're given some information that angle BAE is 32 degrees and angle BCE is 62 degrees, and we're asked to find the measures that we have here. So in letter A, we want to find the measure of angle CBE. That's this angle right here, CBE, this top corner. So we don't have that angle given to us, but we do have this other bottom angle given to us down here, and that one is 62 degrees. Angle BCE, we're told, is 62 degrees. And so if we remember about a kite that the diagonals are perpendicular, then we are going to go ahead and take the acute angles of that right triangle, meaning BEC is a right triangle, and its acute angles are complementary, meaning angle EBC, this top angle here that we're being asked to find, or CBE, and the 62. So here's my equation. 62 plus measure CBE that I'm looking for is going to equal 90 degrees. And so a simple subtraction in that right triangle gives me 28 degrees for that. Then for part B, if we're filling it in, now we want to find angle ABE, so that's that upper corner, the other part to that angle, and so that is going to be using the other piece of information we were given, which to begin with was that this angle here, BAE, is 32 degrees. So if this one's 32, and again even that other side of the right angle is also a right angle, then we can do another subtraction. So the measure of angle ABE plus the measure of angle BAE will always equal 90. Those are the acute angles in that right triangle. And if we substitute 32 for the measure of angle BAE, then we get an equation that ABE plus 32 equals 90. And then the measure of angle ABE with a quick subtraction there has to be 68 degrees. Then let's look at the reflect, number 3. It says from parts A and B, what strategy could you use to determine angle ADC? That's this one down here, ADC. Well, we know, remember, in a kite that the opposite angles here and here are congruent, and we just found what those two smaller pieces of that angle were. So 28 plus 68 is the measure of the top angle ABC, but we also know that that's equal to the measure of the bottom angle ADC. And so if we add those two together, the your turn is going to ask you to determine what the measure of that ADC is, and I think I'll just really quickly do that addition for you because the reflect leads right into it, and of course that's going to be 96 degrees. Alright, moving on to the explain to on this page here. What are we able to know about isosceles trapezoids? So first of all, a trapezoid is a quadrilateral with one pair of parallel sides. I want you guys to actually scratch out the words at least there. It's a little bit more accurate. It's just to say if there's one pair of parallel sides, then we're able to call it a trapezoid. So you can see in the diagram that the two sides that are parallel are called bases, and that the other sides in the trapezoid that are not parallel are called legs. So make sure you know that vocabulary. It's important to know that vocabulary because when we talk about specifically an isosceles trapezoid, the bases are not congruent. So we're going to change the markings on the diagram. You can see that the bases right now have 2 tick marks each. That's a typo. So we should have the bases 2 tick mark on one side, and let's do 3 tick marks on the other here. So remember, these bases are still parallel, okay, but they are not congruent to each other. The legs, however, the legs are congruent to each other, and that's important to know in an isosceles trapezoid. Hope you can see that we have some symmetry happening there in that isosceles trapezoid. Other vocabulary you need to be aware of is that a trapezoid has what we call 2 pairs of base angles. The base angles are the ones at either end of the bases. So if these are my bases, then the base angles are here and here, and here, and here. So we know we have some relationships that we can work through on the next page. Okay, here's some isosceles trapezoid theorems you need to be aware of. And the first one is that if you have a quadrilateral that is an isosceles trapezoid, then each pair of base angles are congruent. So that's what we marked on the previous page. If a trapezoid has one pair of congruent base angles, then automatically it's isosceles. So notice this is a normal and converse pair of those two statements there. The if and the then are just switched. And then finally, we can say that a trapezoid is isosceles if and only if its diagonals are congruent. So if we're just looking at its diagonals and it's a trapezoid, it can only be an isosceles trapezoid if we have congruent diagonals. So we'll look at the congruent diagonal piece in a little bit. We're going to focus right here in this proof on completing the flowchart proof of the first isosceles trapezoid theorem. So that's that each pair of base angles are congruent. So first off, the givens are, number one, we know that it is an isosceles trapezoid, and we know that the top and bottom sides are parallel, and specifically the legs A, B, and CD, or DC, are congruent. Our task is to prove that the bottom angles A and D are going to be able to be congruent as well. Let's zoom in a little bit here so I can write a little better. Okay, so on this diagram we start by knowing that the sides are parallel, BC and AD, that's a given. Then, as we did before with drawing a new line into the diagram when we were dealing with parallelogram proofs, we're going to add a new line into the diagram, and that's going to be line CE. That's going to be drawn specifically parallel and intersecting, parallel to AB and intersecting at point E right here. So that's just the parallel postulate. We haven't really talked about that much, but that's one of those able to kind of put in a diagram, extra lines to help us out kind of thing. Then from there we can say that angle A and angle CED are corresponding angles, because here's my parallel lines, and then that bottom side AD is our transversal. So we'll go ahead and mark those angles as congruent. And to write it into our proof, angle A is congruent to angle CED. And then as soon as we have those angles written in as corresponding, we know that ABCE is a parallelogram by the definition of parallelogram that allows us to have opposite angles congruent. So let's go over here. We'll fill in ABCE is a parallelogram. And if it's a parallelogram, then that means its opposite sides are congruent. So that's our AB is parallel to EC. Again, AB and EC are those, AB and EC are those sides that we force to be parallel. So we're going to mark them as parallel. We're also going to say that since we know AB is parallel, that it's also congruent if it's a parallelogram. So there's AB is congruent to EC as well. Then AB is congruent to DC because we were told that it is an isosceles trapezoid. So there's the definition of isosceles trapezoid. And then as soon as we know that, side EC and side DC are congruent by substitution. And again, that's substitution because they're both equal to AB, so they're equal to each other. Then once we know that we have two congruent sides, notice we've got an isosceles triangle happening over here. So angle CED is congruent to angle D because of the isosceles triangle theorem, and therefore if they're both equal to angle CED, we've got, again, A is congruent to CED, and now D is congruent to CED. So finally, angle A is congruent to angle D. So that's a flowchart proof for that first theorem, that if we have an isosceles trapezoid, the base angles are congruent. The next page we have an explain to go here. And this explain is talking about isosceles trapezoids. We want to talk about how do we use the idea that isosceles trapezoids have congruent diagonals. A to C and B to D are congruent in order to find some unknown values here. So in this case we have a railroad bridge, the picture over on the right, and I hope you can see the isosceles trapezoid structure within those support beams there. And it has side sections, it says, that show isosceles trapezoids. The figure ABCD represents just one of these sections. AC, we're told, is 13.2 meters, so that's this diagonal. And then we're told that this part of diagonal BD, just BE here, is 8.4. What we want to find is what is the rest of that diagonal BE, which is DE. So we're going to use the property that the diagonals are congruent to begin with. AC is congruent to BD. We're going to substitute what BD equals, or excuse me, what AC equals, and then as we substitute what BD equals as the two smaller pieces put together, we've got the known 8.4, and I forgot to write that on the diagram, but let's go back and do that. This part is 8.4, and this whole thing here is 13.2. So diagonals are the same going both directions. So 8.4 plus the unknown DE has to equal the whole length, and then a quick subtraction just leads us to 4.8. On the next page, we're going to have a similar problem. Continuing with this idea of isosceles trapezoids. So we know that trapezoid EFGH is isosceles, and what we want to find is the value of x that makes it isosceles. So the base angles we know in an isosceles triangle are congruent, so that's these angles here, and they're given some algebraic labels. So in particular, the pair at E and F are congruent as we're filling in. So congruent angle E and angle F. The definition, that means their measures are the same. And so we're going to substitute for measure of angle E the 3x squared minus 4. And for measure of angle F, we're going to substitute in the 2x squared plus 21. And we're going to make an equation. And then some quick subtraction there just gets us to x squared, and then adding 4 to both sides is x squared equals 25. So subtract 2x squared from both sides and add 4 to both sides, and then finally take the square root anytime we have a squared variable. Notice we're going to get two values. We want to see if both of them are going to make sense. Both 5 and negative 5 squared will give us 25. So let's look at the diagram. If we're plugging in x back into these values here, these expressions for angle F and angle E, the question is, does 5 and negative 5 both make sense? Well, I hope you can see that because x is squared in both of those expressions, that either one of those answers would work. Okay, you're going to go ahead and do next. Pause the video here and do a couple of minutes on the Your Turn exercises 8 and 9 that are right below there. And you're going to be using those ideas of diagonals being congruent and base angles being congruent to solve for some missing pieces. Okay, moving on, we're going to go to explain number 4. Hope you've done the Your Turns there. In a trapezoid, we can say that there's what we call a mid-segment of a trapezoid. We just got done talking about mid-segments of triangles, so this shouldn't come as a shock here that we are able to find a mid-segment of a trapezoid as well, and that the definition is similar, okay? The mid-segment of a trapezoid connects the midpoints of the legs. Midpoints of the legs is what it connects. The mid-segment has a couple of things that are true about it, as we look at on the next page. The trapezoid mid-segment theorem has two parts. The first one is, if I connect the midpoints of the legs, then they are going to be parallel to both legs, to both bases. So the mid-segment XY is parallel to BC and AD, and also that its length is going to be half, or the average of the sum there, BC plus AD. If I were to average the lengths of those two segments, then I can say that that's what that middle segment XY would be. So 1/2 the sum, BC plus AD. In example 4, we're going to use that idea to find the missing length here for part A. So in EFGH, we're finding XY. We're going to use the second part of the trapezoid mid-segment theorem, which talks about the length. So XY is going to be equal to the average of EH and FG, or 1/2 of EH plus FG. Well, in this case, we're given both of those values, so we're just going to substitute in and crunch some numbers here. 1/2 of 12.5 plus 10.3 is half of 22.8, and that gives me 11.4. Moving on down the page, doing some fill-ins for part B. Again, using the idea of the mid-segment, we're going to go ahead and use that PQ is going to be half of the two bases added together. One of them is KL and JM. The one that's missing appears to be KL in our fill-in here. So we're going to substitute in For PQ, what we know, in this case, we know the mid-segment and we're missing another piece. And then 8.3 for KL. And then wrapping that into the equation over on the right, that'll give us our 8.3 here is equal to 1/2 9.8 plus JM. Now next the book tells us that we're going to multiply both sides by 2. That's to get rid of that fraction of 1/2. And what we do to one side to get rid of 1/2, we got to do to the other. So multiply both sides by 2, we should get the equation 16.6 is going to equal 1/2 goes away, so we just have what was in parentheses there to begin with, which is 9.8 plus JM. And then we're going to subtract the 9.8 from both sides, and we get 6.8 for JM. Okay, last little bit of this video, guys. You're going to do the Your Turn number 10. Make sure you log on and check all the Your Turn answers before you come back to class tomorrow.